Welcome back. Today we're going to discuss Chapter 27, wherein we learn about some more tests of significance. Specifically, we look at some tests for averages. There's a couple of nuances that we'll look at, but remember as we're doing this that the overall process remains the same. We're still using the hypothesis testing model and our steps for testing a hypothesis. Now, these are just some different variations on that theme in the sense of we're still hypothesis testing. We're just looking at a couple different tests that apply to different research scenarios. Nope. All right. The first thing we need to consider is how to calculate the standard error for the difference when we're comparing two samples. So previously, and this is the main point of this chapter, is that we are looking at comparing two samples. Two sample means, whereas before we were comparing one sample to an expected quantity. When we have two independent chance quantities, we need to use a different method to get the standard error, and we call this the standard error for the difference. And you see here we have a little example where we have two boxes, and you can see they each have a different average, and 400 samples are taken from the first box. That's our sample size. 100 are taken from the second box, box B, and we get the difference between their averages. Remember, we get this is just a rubric that just tells us basically the average here, value plus value plus value divided by the number of total draws in the data set. So it gives us the average. So we can get the difference between these two averages, and we need to get the standard error for that difference too. One thing to remember here is that this only applies when we have an assumption of independence, and you won't see many dependent situations in this class, although we will discuss it briefly. These are independent groups. This could be called in other places an independent groups situation. And the problem is how to find the expected value and the standard error for the difference between these two sample averages, because how do we know what the expected value would be in this case? We don't have a previously established value to refer to, either a previously established value based on research or based on some ideal model we're testing against. The first step is to compute the expected value and standard error for each average separately, and the next problem is how to put the standard errors together. People often think that you should add the standard errors, but that's not a valid solution mathematically because it ignores the possibility of cancellation in the two chance errors. Just as when we get deviations from the mean, we have to treat them mathematically with a square in order to remove the sign. We're going to do a similar process here for the standard error for the difference. And we can quantify the standard error for the difference as the square root of the standard error for the first quantity squared plus the standard error for the second quantity squared. So previously, a sample average, remember, was compared to an external standard. Now we have to compare to, now we have to compare to another group. So we don't have an external standard, and the difference of their averages is the issue. Both averages are subject to chance variability, and the standard error for the difference needs to take that into account. The null hypothesis says the averages for the two boxes are equal, but on that basis, the difference between the sample averages is expected to be 0. And the observed difference just represents the luck of the draw. Now, this is the same as what we were discussing before. The null hypothesis is always says that difference is due to chance variability. The alternative hypothesis says the opposite. It says in this case that the average of, now we're looking at our sample boxes here, you can see that we're comparing the 2004 data to the 1990 data. And this is an example from your book where they're comparing the score on a reading literacy test for 17-year-olds in school in 2004 and 1999. We've got 1,000 draws from each of these populations. Each ticket has the score. But as you can see, there's a different box for each group. And so the alternative hypothesis for this model, well, our null hypothesis would say that any difference observed between these two groups is due to chance variability. The groups are the same. That's what the null hypothesis says. Our groups are the same. The alternative hypothesis says that the average of the 2004 box is smaller than the average of the 1990 box. Thus, reading scores really did go down, and that's why the two sample averages are different. And we can use our two sample Z statistic to help us choose between these hypotheses. The two sample Z statistic is, as you can see, incredibly similar to the Z statistic we had before, except now we have the observed in difference minus the expected difference, and the SE for the difference. So this is all just recast in terms of the differences, and you need the sizes of the two samples, the averages of the two samples, and the standard deviation of the two samples. So you need to have all that information in order to use a two sample Z statistic. Remember that the standard error for the difference in this of two independent quantities is the square root of the standard error for the first quantity plus, the square root of the SE for the first group squared plus the SE for the second group squared. So I included that in there to help you. You can use this as a guide to thinking about the two sample statistic. There's a bit of a discussion before we go to that in your book about treating the two samples as independent and drawn with replacement, about treating the samples as independent or dependent. For our purposes, when we've got separate we can still make the assumption of independence. So even though the control and treatment averages can be thought about as mathematically dependent in some ways, really for our purposes, ordinarily treating the two samples as independent and drawn with replacement will give you an excellent approximation for the standard error for the difference between the averages. We can also apply that the two sample Z statistic to an experimental situation. So the two sample Z statistic can be used to analyze experimental data, but only when there's random assignment to treatment and control groups. If there's not a randomized controlled experiment, then you can't use the Z statistic here. So that's the key piece there. And you can conceive of that idea as a box where there's a ticket for each subject, and the ticket has two numbers. Their response to treatment A, their response to treatment B. So it's got both on there, but you can only observe one of the two numbers. You observe them through the assignment to groups. I know this is kind of a funny way to think of it. You might be thinking, well, don't they get the treatment after they're assigned to the group or the control? Sure, yeah, that happens there, but this is a theoretical idea of way of conceiving of the population box. So in this case, your two groups are the treatment and the control group, or you could compare two treatments. Remember, control is really just another, you're just comparing two interventions. And the SE for the difference between the two sample averages is conservatively estimated through computing the SE for the averages as if the draws were made with replacement. This whole point here, which I'm kind of skipping over, is that the tickets are drawn without replacement from the box, but we can still conservatively estimate the SE by computing them as if they were made with replacement, which is easier to do. That's why we'd want to do that for a number of reasons. And just hold on for a minute. And we can combine and then based on that assumption, we can combine the standard errors as if the samples were independent. So when should you use the Z-test? Well, you shouldn't use the Z-test when the two correlated responses are observed for each subject. So if you know you have two responses that are correlated, then the Z-test isn't appropriate. We know there are other tests for that scenario, and we can apply the correlation and regression model. We can do it within hypothesis testing as well, with just a small addition to our previous discussion. And so we remember that the Z-test applies to two independent samples, and the formulas can give the wrong answer when they're applied to dependent samples. But unless we are talking about a treatment and control groups and a randomized controlled experiment, in that case, we can still use the dependence assumption or the independence assumption and go ahead and use the Z-test. I've got to warn you that there's also a second two-sample test, and you shouldn't be shocked to hear it's a two-sample or a two-group independent group t-test. When do you think you might use a Z-test versus a t-test in this context? Well, if your sample sizes are small, then you would use the t-distribution, whereas if they're large, you'll use the z-distribution. And this applies more to our subsequent discussion about the hypothesis testing in SPSS. They distinguish the tests a little bit differently, but the key thing to remember is that when you have a lot of samples, the t-distribution converges into being the same as the normal curve. So even if you do a t-test, if you have a very large sample, it should still come out equivalent to a z. In summary, the expected value for the difference of the two quantities is equal to the difference of the expected values. So we can get the standard error for the difference of our two independent quantities, as we saw earlier. We just have another standard error formulation to use. And the tests based on the statistic in this chapter are two sample z-tests. We can also use a two sample z-test in situations where you classify and count by putting ones and zeros in the boxes, just like we did before. And we can use the two sample z-test to compare treatment and control groups, averages or rates in an experiment, as long as random assignment to groups was utilized. So the two sample z-test gives us a lot more options, or it expands the options for research scenarios we're prepared to evaluate. So before we could compare our sample to a population parameter, expected value, now we can compare our two groups to each other. You'll see that we can also compare more than two means, averages. Now, I won't expect you to do by hand this test, but an analysis of variance test, or an ANOVA, enables you to compare three or more independent groups. There's also ANOVAs for other scenarios, but just to give you an overview here, if you had three or more independent groups, you could still compare their averages. You would, instead of using a z-test, you would need to use this test called an analysis of variance, which still compares is still a test for an average, even though it's called the analysis of variance. It's actually comparing the group means, just like we do in the z-test. And although we're not going to cover the mathematics of the test here, it's conceptually very similar. And we will see how to do an ANOVA in SPSS, because some of our so you'll get a little bit of experience with seeing just a scenario where you might use that test. In our future lecture on the hypothesis testing with SPSS, and we'll also have so as you can see, we have options for how to analyze our data. The key thing is to model the data correctly in terms of your box model and understanding what the null hypothesis is. We'll give you a good guideline for determining which test to use. And when you're making your decisions, may the odds be ever in your favor. Or maybe we should remember Ben Franklin instead. Diligence is the mother of good luck. So the odds don't really matter if they're in your favor or not. You can always exceed the odds through diligence, or almost always.